Morning. We've been looking at using multi-stage op-amps to improve the performance. Performance here, by that I mean DC gain, right? DC gain reduces the steady state error with constant inputs. Of course, now the topology has changed and the poles and zeros have changed. So that means it will have, the stability implications will be different. Okay. So we can consider a two-stage, what is called the Miller compensated op-amp. Block diagram wise, it looks like this. And in this case, I'm going to ignore the output resistance because my focus right now is on stability and settling and so on. Okay. This is the output C1, C2, and C. We don't have to worry about the expression in terms of the component values, but we do know that the gain of the op-amp, which is the gain from its input to the output, will be of this form, right? And there will also be a zero, which I will ignore for now. Okay. We know what the zero does, and in any case, we will take it into account later. And then we also have the two-stage feed-forward amp, which looks like this. You have two paths in parallel from the input to the output. Okay. And you have some load capacitor CL, let's say. Then you have C2 here. This is GM1, GM21, and GM22. Okay. So in this case, the op-amps transfer function will be of the form, what is it? Omega u by s, 1 plus Z1 by s, okay, which can also be written as omega u Z1 by s square, 1 plus s by Z1, okay. So it has a 0 in the transfer function, right? Now the difference between the 0 in this and the 0 in that one, I was able to ignore it here, but I won't be ignoring it there. Why is that? Anyway, we'll see. Why is that one? This is a non-dominant 0. It's supposed to be. That is after the unity loop gain frequency, whereas this will be before that. Okay. So now let's look at the op-amp gain by itself, which again, as I've said many times, it corresponds to the loop gain when you have it in unity feedback. We'll consider the non-unity gain, non-unity feedback later. Maybe I'll just not selecting for some reason. Okay. Okay, so now if I sketch the Bode plot of this, in the two cases, what will I see? So in this case, in the first case, for the Miller compensated op-amp, what will the Bode plot look like corresponding to this function? So initially it will fall at minus 20 dB per decade, which corresponds to basically just omega u by s, right? And this will be omega u. And we expect the poles and zeros to be after the unity gain frequency. So anyway, let me just show the unity feedback case because the loop gain is what is relevant. So in this case, basically the loop gain is the op-amps transfer function. Okay. They are the same. Now, if I take into account only the second pole, it will do that. This is P2. Now, if I also take into account the zero, of course, the zero could be before or after. I'm showing it as being after that. It will look like that. So basically, these are non-dominant. Again, I think you have seen techniques for getting rid of that zero Z1, right? There are some circuit techniques you can use, but the non-dominant pole will always be there. Okay. Now, what will the loop gain look like in the other case? For the feed-forward op-amp, what will the loop gain look like? Yeah. So basically, let me try to sketch it with approximately the same omega u. So what happens is, a couple of different ways to look at this. Maybe easiest way to sketch is to split this as omega u by s plus omega u z1 by s square. Okay. So omega u by s looks like this, and omega u z1 by s square, let's say it looks like that. Okay. So the overall transfer function will be, it will start like that and then do that. Okay. And this will be Z1. Okay. So this will start with a minus 40 dB per decade slope and it will switch to minus 20. Now, as you know, these are all different ways of saying the same thing. The Nyquist plot, in which quadrant should it enter the unit circle? Or reasonable stability margin? In which quadrant is it? Third quadrant, right? That's what it always does. Okay. And essentially, let me also sketch the phase here. What will they look like? What will the phase look like in the two cases? In the first case, what does it look like? It will start from minus 90 and eventually reach minus 180 if you have only the pole. If you also have the zero, it will go to minus 270. Okay. This is a right half plane zero, right? So it will go to minus 270. So at P2, And if I also include the 0, it will do something like that and go to minus 270 degrees. Okay. What happens in the other case, in the feed forward op-amp? What happens in the other case? Starts from minus 180 and it will do that and eventually reach minus 90 degrees. So basically the point is, wherever, what does it mean to say that the Nyquist plot enters the unit circle in the third quadrant? At the unity loop gain frequency, the phase must be between minus 90 and minus 180, right? So that's the meaning of entering it in the third quadrant. And actually, when you have this distinct, I don't know if you are familiar with this. Are you familiar with what are known as minimum phase systems? Basically, you have only poles and zeros only in the left half plane. Okay. In that case, actually, you can get the magnitude plot from the phase plot and vice versa. Okay. So you don't even need both of them. So the point is, if you have this phase to be between minus 90 and minus 180, the magnitude will have a minus 20 dB per decade roll off. Okay. So essentially, it will have a first order behavior. Okay. So you already know this. I think when you, for a stable system with reasonable stability margin, at the unity loop gain frequency, the magnitude should cross unity at minus 20 dB per decade slope. Okay, that's the same as saying the Nyquist plot should cross it in the third quadrant. Okay. So finally, I mean, this is also why I like the integrator description. We started with integrator as the element to be used in the negative feedback system. Then essentially you have a first order loop gain, right? You have this minus 20 dB slope everywhere. But even if it is not everywhere, at the crucial point where it crosses unity, it has to behave like an integrator. Okay. The bottom line is, to make a stable feedback system, you can only have one stage in feedback. Okay. So what happens really is that around the unity loop gain, you have two stages to provide high DC gain, but these are basically dead by the time you come to the unity loop gain frequency. You have only this part in feedback. Okay. Similarly here, what happens around the unity loop gain frequency? Yeah, basically you have that in feedback, something like that. Okay. The second pole is further away. Somehow, one way or the other, you should have only one stage in feedback. Okay. So if you have multiple high gain stages and have a single feedback loop around all of them, it tends to be unstable. It may be outright unstable or it may ring heavily. Okay. So typically, any stable feedback system, even if you have multiple stages, there will be one overall feedback which is taking advantage of the very high gain. Very high loop gain is essential to reduce the error. Error meaning the virtual short voltage, right? But to stabilize it, you need to have multiple local feedbacks. Okay. So in general, the scheme may look like this. Okay. So you could have, I'll just show this schematically. This is not very important here. You have some feedback loop like this with many stages, but this will be terrible for stability. So if you do this, you will end up having to do something like this, introduce feedback from different places, or you may have to do something like that. Okay. So finally, you will end up with, at very high frequencies, only one stage in feedback. Okay. And there can be many other pictures also that are possible. But one of the ways of thinking about it is that the Nyquist plot should enter the unit circle in the third quadrant, which is the same as saying the loop gain should have first order behavior around the unity loop gain frequency. Beyond that and before that, it can do anything. Okay. So that is, the loop gain ideally, according to our picture, would be an integrator. Okay, this is the unity loop gain frequency. Now, in reality, around this, it has to be like that. Okay, so before that, it can do whatever. After that, it can do whatever. Okay. So this is yet another way of simply saying that the Nyquist plot should enter the unit circle in the third quadrant. And the block diagram way of looking at it is around the unity loop gain frequency, there is actually only one stage that is relevant, that is active in the feedback loop. Okay. So bottom line is we can only have one stage with stability, and that's what we'll eventually have. Okay. Is this fine? So now we have these loop gain shown. I mean, reality, of course, we don't have infinite DC gain. That is, we will have output conductances. So what really happens is, I'll just show it on the same plot. So let's say this is the DC gain value. It will get limited to that. So as you go to lower frequencies, both these curves are showing that the op-amps transfer function is going off to infinity. It won't go to infinity, it will go and flatten out at the DC gain, whatever the DC gain is. If I assume the same DC gain for the two, this will flatten out like that. Is this fine? So now, which of these is a better op-amp? Again, I am only considering the unity loop gain case for now. Which one is a better op-amp? Huh? What do you mean? No. We'll assume that, see, after omega u loop, the negative feedback is inactive. You may have signals there, but we will not be, I mean, that is not our intended frequency of operation, right? Yeah, because then it's open loop. We are making negative feedback circuits, right? So obviously our, for it to operate effectively as a negative feedback system, our signals will be well below the unity loop gain frequency or below the unity loop gain frequency. So which one is better? Or you can't tell? Okay, so if you look at it beyond this point, right, both of them, the way I have drawn it, both of them are the same. Okay, if I assume the unity loop gain frequency is the same, both of them will be the same. But below this one is providing higher loop gain. So is it of any relevance? Huh? Okay, what will be better? Error will be lower. So what happens? What are all the advantages of having lower error? So one is, I mean, the error is lower means the output is closer to the input. Okay. And it does make everything better, the higher loop gain. So in one of the assignments, you had solved this, right? I would forget the exact, what was it? Let me see. Yeah. So you have this problem, okay? Let me just show this as A of S, okay? And then well, maybe that is not the most relevant example here. So what happens is, of course, it is true that the larger the L of S, this difference VE, the larger the loop gain magnitude, smaller the smaller the magnitude of VE. Okay. So of course that means VI and VFB are closer to each other, and this happens. I mean, this is related to many different things, including distortion. Okay. So that is, this A of S itself obviously will make them with transistors. It will be nonlinear. Okay. Now, if V is smaller, it means that you are driving that nonlinearity with a smaller amplitude. So that means also that the nonlinear products will be substantially lower. Okay. So that problem I tried to, that's not in exactly the same form, but there also you would have seen that the nonlinear product would be suppressed by the loop gain. Okay. So the smaller the error, the lower the nonlinearity. Okay. Because you are driving the nonlinear stages with a smaller signal. Okay. So if you reduce the signal by a factor of 2, the second order nonlinearity reduces by a factor of 4, and the third one reduces by a factor of 8, and so on. Okay. So it also reduces, higher loop gain also reduces the nonlinear products. Okay. I mean, depending on where the nonlinearity is produced, but basically higher loop gain helps in many ways. So this feed forward op amp, this feed forward op amp, right? So it provides a higher loop gain in some range of frequencies. Now, if you have a third order op amp, that is 3-stage op amp, what happens is, in the Miller compensated op amp, basically it will still show a first order behavior, dominant pole behavior, but it will have a higher DC gain. Whereas this one, what happens is, it will start with minus 60 dB per decade, then minus 40, minus 20. Okay, so it goes to very high loop gains in some range of frequencies. Okay, of course, the closer you go to omega u, it becomes nearly the same as the, right? So in that sense, the feed forward op amp is better. Okay. Now there is also another case which I'll just mention, which you may or may not appreciate immediately. So this is again something related to the, I think you already solved this problem, right? Where I had given a GM with some inherent capacitances that depend on the process. Okay. Now, in any process, you make any block, it comes with its own parasitic capacitors. The transistor comes with its own CGS and CGD, which includes both the inherent CGS because of the gate capacitance and any extrinsic CGS because of overlaps and contacts and so on. Okay. So now that means that the technology inherently puts a limit on how fast a circuit or how high a bandwidth you can achieve, right? So in this particular case, I had asked, I think I had given a unity gain feedback, right? CL, this is CI and CO. And I had said that, just for simplicity, CI and CO are both, what is it? GM by some transit frequency omega t, where omega t is a parameter of the process. Okay, I'll explain what that is with the transistor. In fact, that's commonly used to characterize the process. But the point is, the higher the omega t, the smaller the parasitic capacitor for the same GM. Okay. So now what was the result of this? What was V0 by Vi? Do you remember? What do you get? Or at least the denominator. The denominator, basically, you can, this is what is the order of the system? When it's driven by a voltage source, what is the order of the system? You submitted the assignment just like a few days back, right? I thought you would remember the expression also. What is the order of the system? Yes, Ankit. What is the order of the system? What is it? 1. Yeah, because you have the voltage source. If you short this, basically all 3 capacitors are in parallel. Okay. And where is the pole? So we'll have something divided by 1 plus S by P1. Where is this pole? What is the resistance that you see? What is the capacitance that you see? In a first order case, you should be able to find out the pole or the time constant just by inspection. So what's the resistance that you see? 1 by Gm. So the conductance is Gm. What's the capacitance? Cl plus C0 plus Ci, which is basically 2 times Gm by omega t. Okay. So now what you want to find out is what is the Gm required for some value of P1. Okay. What will be that expression? This is what you found out, right? Okay. So basically, if you rearrange this, you get Cl by Gm plus 2 by omega t. This is equal to 1 by P1, right? So what do you get G1 to be? Okay. This is the expression you would have got. Okay. So now this is a useful way to understand what happens to circuit design with technology, right? I had asked you to plot the bias current versus the pole frequency, right, that you want to achieve. P1 is roughly like the bandwidth of this. Of course, you also have a 0, but P1 is the pole of the system. So that is like the bandwidth. So what I want to find out is to get a certain P1 value, what is the Gm? And the current that you will burn will be proportional to Gm. So you can plot Gm versus P1 or current versus P1, you will get the same thing. So what kind of dependence do you get? What is it at very small values of P1? What is it? So when P1 is much less than omega t. Omega t is some sort of speed limit of the process, right? When you're operating well within the speed limit, you will get P1 times CL, that's all. Okay. So it is just linear. But what really happens as you approach, in this case, omega t by 2? So basically for very small values, it will follow this and then it will just blow up. Okay. This is in general what you expect with any circuit, right? Given a process, you try to make a circuit for higher and higher frequencies. It could be amplifiers for higher and higher bandwidths, latches for higher and higher data rates. To do anything, what happens is at very low frequencies, the power dissipation will be proportional to the frequency of operation. Okay, some things have to keep constant. In this case, the noise happens to be constant. Okay, so if you make an amplifier for some bandwidth, right? The power dissipation will be proportional to the bandwidth. Okay, but as you go on increasing the bandwidth, the power starts increasing super linearly. That is like more than in proportion. And you will find that beyond a certain speed, you can't make the amplifier at all. Okay, in a given process, right? So now if you had another different process with a higher omega t, what happens is the same curve would follow this linear for a extended frequency range. Okay, and then you get this. So this is sort of the technological advantage. So sometimes you may have to exploit this. That is, you find that you simply cannot make the circuit work at a certain frequency or a certain bandwidth, or it could be that you can make it work, but the power is astronomical, right? If you are operating somewhere here, then the power dissipation is much more than in proportion to this. Okay. So in that case, going to a better technology, that is something which has a higher omega t, could help you. Okay. Is this fine? So this is some general feature of the process. Basically, what happens is that to get what you have to do for a given CL, to get a higher pole frequency or higher bandwidth, you have to increase GM. Now, if you increase GM, these capacitances will also increase. Beyond some point, what happens is that these capacitances will actually dominate the load capacitance. Okay. So if you are operating somewhere here, what it means is that the load capacitance is negligible. You could probably just remove that. Nothing happens. Only thing is that even if you had CL equal to 0, what will be the pole frequency? GM by 2 I mean GM by CI plus C naught. Okay. So that means basically omega t by 2, right, in this particular example. So even if you don't have any load, you will have omega t by 2 as your limiting bandwidth. Now this omega t, there is some particular quantity called omega t. It doesn't mean that you will make amplifiers up to that frequency, but it's more like an indicator. If you have two processes, one with omega t of 100 gigahertz, the other one with 200 gigahertz, you are obviously likely to be able to make higher bandwidth amplifiers using the 200 gigahertz omega t process. I mixed up terms a little. Omega is in radians per second. This is 200 gigahertz means times 2 pi. You make it. Okay. So essentially, the circuit itself becomes so large that its own loading will limit the speed. Okay. Is this fine? So I'll connect this to the op-amp case later, but basically I wanted to show you this, and this was the point of the problem, to realize that there is some speed limit. Okay. So now what happens in a transistor? In a transistor, you will also have basically CGS and CDB, and also you will have CSB and so on. Okay. So these are due to diodes, and this is due to the inherent operation of the MOS transistor. I won't show CGD, it is negligible in the saturation region. Okay, the inherent CGD. The part due to interconnects and overlap, that will always be there. So essentially, these, of course, in reality, these will not be, I mean, this input side capacitance and output will not be exactly equal to each other, but they'll be comparable. Okay. And both are proportional to transistor width and so on. Okay. So the model that I have shown is correct. That is, any GM that you make, it will have some input capacitance, some output capacitance. And in some sense, they will also be proportional to GM, because to get higher and higher GM with the same VGS minus VT, you will go on increasing the transistor width. And if you go on increasing the transistor width, those capacitances also increase. Now, based on this, there is a particular sort of figure of merit of the process that is defined. It's very similar to what I showed. So you can think of it in two different ways. You can think of the current gain of a single transistor common source amplifier. Okay. And I'll ignore everything else. I'll have only CGS, and the output is shorted. Okay. In fact, you get the same result if you assume that you have a common source amplifier that is loaded by another common source amplifier. Okay. So now if you what will be I naught by I in this case? What is it? Gm by, yeah, Gm by S CGS. What will be V naught by Vi in this case? This is VGS, this is Gm VGS. What is V naught by Vi? Yeah, it's just minus Gm by SCGS, that's all. So the magnitudes are the same for the two. Okay. So if you plot this, the Bode plot of either one, what do you get? What will it be? It's again minus 20 dB per decade. And what's the unity gain frequency? Gm by CGS. Okay. This is called the transit frequency omega t. Roughly speaking, basically this is the frequency up to which you can get gain from a single transistor. Okay. You can, it's either voltage gain or current gain. The current gain definition is used because bipolar transistors came first, and bipolar transistors were traditionally described by the current gain. The DC current gain is beta. Did you have bipolar transistors in some course? Both circuits and devices, I guess. So the DC current gain is beta, but at high frequencies, it goes as Gm by SCGS. Okay. So this omega t, this is called the transit frequency, and Ft, which is basically omega t by 2 pi, okay, which is Gm by 2 pi CGS. This is given as some figure of merit of the process itself. Okay, the process, and then it also depends on the device dimensions. Now, if you operate the transistor in the strong inversion region, what is the expression for Gm? What are let me use this expression, mu Cox, doesn't have to be NMOS, mu Cox VGS minus VT, and sorry, W by L. Okay, and what is this? What is CGS? 2/3 Cox WL. Okay, so what do we get? This is some numerical constant. This is mobility. Mobility indicates the speed of carriers, so it makes sense that this frequency is proportional to mobility. Okay, so if you go to materials which have higher mobility, you will have a higher transit frequency. This is also the attraction of technologies like GaN, gallium nitride, which you may have heard of. There is a lot of hype on gallium nitride right now because of its advantages with mobility. And then VGS minus VT by L square. Okay. So now if you want to design high bandwidth circuits, what is in your control here? VGS minus VT and L, right? You can choose the transistor, you can choose the operating point. How would you choose them if you want to design as high a bandwidth amplifiers as possible? You have to choose high VGS minus VT, obviously, and you have to choose the shortest length that is possible. Okay. So essentially, high VGS minus VT and short length. What does it mean? You just pump a lot of current into a small transistor, it will react very quickly. Okay. So that's what it is. Now you can also see the trade-offs, right? I mean, in a very general sense, without going into specifics of the circuit, the goal of any circuit is to realize high precision, the low power, and high speed. These are like the holy grails of circuit design, right? Now, do you see any conflicts between the three? What is it? So for high speed, what do you need? Small transistors, in particular, small length, high VGS minus VT. Okay. What does this contradict with? Power for sure. So this means high power. It also, what does it say about precision? Use small transistors, random mismatch will be higher, right? So, and flicker noise will be higher if you reduce the transistor length. So there is a direct trade-off between trying to get high speed and trying to get high precision. Okay. Right. So, and then this L in a given process, you try to choose as small an L as possible. But then, of course, there is a minimum limit to the length. By the way, I should have worded this more precisely. This is the FT of the transistor of whatever length you choose. FT of the process will be given by 3 by 4 pi times mu, and this is the best case you can get. You use the minimum possible length, and then this VGS minus VT, that again you have to choose. But when the technology people give you this number, they don't know what you will choose. They will put the highest possible number here, which will just be the highest possible bias, which is VDD. Okay. So this is some number that is given, and this number could be in the hundreds of gigahertz for the modern processes. But in reality, first of all, you cannot bias a transistor with a VGS equal to VDD, right? Then there will be no room for anything else. So your VGS minus VT will always be much smaller than this. So which means your FT will be correspondingly smaller. And for other reasons of let's say precision or noise, I mean mismatch or noise, you may have to use longer channel transistors. Also, the other thing is that if you use short channel transistors, the inherent gain of the transistor also reduces because GDS is a lot. So that may be another reason why you are using long channel transistors. So your FT will be a lot less than this. Okay. Yes. Right. Correct. No, no. Yeah, this is because of random mismatch, right? Yeah. So there was no question of mismatch. Here also, of course, I think you are mixing up two different things. If you remember the expression for signal to noise, it was proportional to the bandwidth, and the expression, the power dissipation was proportional to the product of bandwidth and signal to noise ratio. So for a given bandwidth, you increase the power dissipation, you will increase the signal to noise. Here we are talking about increasing the bandwidth, right? Huh? No, no. If you in that expression also, if you increase the bandwidth by a factor of 2 and keep SNR the same, still the power increases. Okay. So the power can be increased either to increase the speed or increase the signal to noise ratio. Okay. So it's the product of the two. Now this GM by GDS and so on are like practical considerations. That doesn't consider anything like that, right? That assumed ideal op-amps. It assumes that you can make the op-amp, or you also work it out for some passive circuit, this RC circuit. Here, the thing is, even with ideal op-amp models, if you double the power dissipation, you can double the, that is double the GM values, you will double the bandwidth. All that is fine. But the question is whether you can operate with that, the smallest channel length in a process, because then each stage may give you a gain of 10. So then with two stages, you only get a gain of 100 and so on. Okay. So that is more practical consideration. And it's also technology dependent. Okay. In some cases, I mean, in some processes, you may have higher gain, in some you may have a lesser gain. Okay. So this is something to keep in mind. This FT is given as some parameter. It doesn't mean that if you have 100 gigahertz FT, you will be able to design circuits up to 100 gigahertz. What the better way to interpret it is, if you have two transistors, one with 100 gigahertz FE, another with 200 gigahertz, you are likely to be able to design higher speed circuits with the second one. Okay. So this example should tell you like what really happens as you try to increase the speed. Okay. So at very low frequencies, it will be linear. It should be. Okay. And then after that, it becomes super linear. Now we won't have time to go into those things, but at the architectural level, sometimes you will see that instead of operating a single path at some speed, let's say 10 gigabits per second, you may be operating two parallel paths at 5 gigabits per second. So this looks like fundamentally, why would you use two circuits instead of one? Why would you do this? No, I know it can be done, right? But why should you do this? Huh? So basically, wherever you find this type of super linear dependence, right? Power is increasing more than in proportion. So that means that if you reduce the speed of the circuit by 2, you are actually reducing the power consumption of each one by more than a factor of 2. And even if you use 2 of them, you are still better off than before. Okay? You understand? So if you have a super linear dependence on of power on the frequency, if you are able to use, let's say, two circuits at half the frequency, it seems like it's the right thing to do. Okay. Whereas if you are operating here where it is linear, there may not be an advantage in this respect. There may be other reasons. I mean, there are many reasons why you make architectural choices and so on. But if the power is exactly proportional to frequency, then splitting it into two parallel paths at half the speed doesn't really buy you anything in terms of power dissipation. Whereas if the power is going more than in proportion to frequency, then it makes sense to do this. Okay. So this is why in many cases you will see that and digital circuits, it is the same thing. So when you see some let's say terabit per second or 100 gigabit per second data path, it's not that you have a series of flip-flops clocking at 100 gigabits per second. Okay. So there may be 64 parallel paths, each one operating at some 1.6 gigabits per second or even more. I mean 128 paths and so on. Okay. So the aggregate data rate will be something because beyond some point you can, I mean, any digital circuit also you take, you will have the same dependence. Okay. So you make, let's say, what is the standard thing? You make a register. You know what a register is, right? It's used for storing data, and you can read and write data out at certain speed. That's the clock speed. So you try to go on increasing that in a given process. You will see that beyond some point, the power dissipation increases more than in proportion to clock rate, and beyond some speed, you can't realize at all. Okay, in a given process. So there, what you do is you have many parallel paths, each one of which is operating at a lower rate. Okay. So this is some general things about technology. This was also the motivation behind asking this question. Okay. Now coming back to this op-amp, one advantage we already saw. This has a higher loop gain. Okay. Now the other thing is that if you see, at least in this form, there is nothing here beyond omega u loop. That is omega u loop. After that, there are no other parasitic poles and so on. Okay. Whereas here, after that, there will be P2. Okay. So now if you look at these op-amps also and ask what is the highest unity gain frequency op-amp I can realize, right, using either the Miller compensated topology or the feedforward topology, which one will it be? The thing is that these parasitic poles are roughly like Gm by C, right? They are related to the inherent speed limit of the process. Okay. Because again, you know that the non-dominant pole here is proportional to Gm2 by these parasitic capacitors. But if you go on increasing Gm2, what happens is the C1 and C2 will go on increasing regardless of what load you have connected. Okay. So roughly speaking, whenever you have these parasitic poles, you can imagine that there is a frequency beyond which you cannot push them. Okay. So on paper, it's fine. If I want omega loop of 1 megaradian per second, I'll have the second pole at 4 megaradians per second. If I want it at 1 gigaradians per second, it will be at 4 gigaradians per second. But in a given process, you may not be able to push it beyond some value. So that kind of sets what is the maximum omega u loop you can have. Okay. So whereas in this case, you don't have anything. In reality, there will be some other junk, but the highest possible unity loop gain frequency is higher for the feed-forward op-amp compared to the Miller compensated op-amp. Okay, so that is also another advantage. Is this clear? So the feed-forward topology, because of its higher order behavior at lower frequencies, it gives you loop gain advantage, and it also gives you the speed advantage. So, but why don't we use it? Why is this not taught in analog circuits? So that I have a job, right? I can also teach this course and draw a salary. Why not? Yeah, that is definitely true. And you can also look at, that is very much true. So again, we will continue this, but this is the op-amps transfer function, and it is also the loop gain if you have it in unity feedback. If you have, let's say, a non-inverting amplifier of gain K, what will be the loop gain with the same op-amp? I mean, what happens to these loop gain curves? What happens? Move? Where? Sideways, upwards, downwards? It will move down by a factor of K. So what happens to the stability margin on the left one if it moves down by a factor of K? It improves or remains the same if it's already good enough. What happens to this? Clearly, I mean, this 0 becomes closer to the unity loop gain frequency. Sufficiently down, where it crosses unity, the slope will be minus 40 dB per decade, right? If you move this down sufficiently, that's what is going to happen. So stability is going to definitely get worse. Okay, that is for sure. So that is one reason why you don't, whereas the Miller compensated op-amp, it's easy to use it as a general purpose op-amp, the kind of op-amps that you buy in the lab. If you use it for any gain, more than one, I mean, gain usually means 1 or higher, you will be fine. As long as they have ensured that it is unity gain compensated. In fact, if you have seen the data sheet, it also says unity gain compensated. Okay. Whereas the second one cannot be used like that. But in addition to that, is there a disadvantage? Please think about the advantages that we mentioned, and then you can work out what the disadvantages are. You can also look at, I think in the previous assignment, you worked out the closed loop transfer function of this also, right? So even from there, you can see what the disadvantages are of the feed-forward op-amp. We'll discuss them, but they are actually useful for a particular class of circuits. I'll also talk about. Okay. Any questions?